Yeah. Please wait, sir. 2 or 3 minutes. We will begin the session.
Okay, okay, okay.
Uh, can you share the screen, sir?
Okay, okay.
We will verify once. Yeah. Okay, sir. It's a full screen now. Okay.
ఎందుకు 120 అయింది 122 మా రోజు 80 90 ఉండేది
Good evening to all. So I welcome you for KSRM faculty lecture series. So continuously with your support, we are conducting this event, and I request all the faculty members. The recorded videos are available. I shared you the folder link. So the same link you can pass on to the students, and you can ask them to have a internship with concerned faculty members. So almost 15 to 16 video lectures we completed, and so the students, they can come and have an internship, and they can complete it, and the same they can showcase, or they can submit to the department. Today, Dr. M. Murli Dr. M. Murli, Associate Professor, Department of EEE, is going to deliver on genetic algorithm and its applications. So now handed over to Murli sir.
Good evening, sir. Thank you for your introduction. So today I want to give a small presentation on genetic algorithm and its applications in our engineering studies. Am I audible, sir? My voice is audible, sir? Hello?
Yes, sir. Yes, sir.
Okay, okay. So let us start. What is genetic algorithm? First, before going to genetic algorithm, so it comes under optimization. So genetic algorithm means nothing but it is optimization. So what is optimization? It is the mathematical procedure for finding the maximum of a function or minimum of a function. So this is called optimization. An optimization algorithm is a procedure which is executed iteratively by comparing various solutions till an optimum or a satisfactory solution is found. Okay, this is a general optimization algorithm. Okay, this is the general basic steps, basic procedure we can find in every algorithm. Okay. So the classical optimization techniques are useful in finding the optimum solution or unconstrained maxima or minima of continuous and differentiable functions. Okay. The classical methods have limited scope in practical applications as some of them involve objective functions which are not continuous and are differentiable. So for this type of objective functions, that means it is a nonlinear objective functions. So mainly for nonlinear objective functions, the classical methods have some limitations. So we are not using classical methods for basically for the nonlinear optimization problems. Okay. So basically we have some four types of, sorry, I have written 3 here. So 4 main types of problems can be handled by the classical optimization techniques. That is single variable single objective functions, multivariable single objective function with no constraints, multivariable single objective function with both equivalent and inequality constraints, and a multi-objective functions. So these are the different types of objective functions are available. So these objective functions we have to do optimization. So in the optimization we are having, two categories basically. That means the optimization methods are divided into 2 categories. That is traditional optimization and another one is non-traditional optimization. So here traditional optimization nothing but another name of traditional optimization is nothing but classical optimization. So classical optimization have some limitations. Just now I told you. So these classical optimization methods we can have some limitations regarding my nonlinear objective functions. Okay. So that's why we are going for non-traditional optimization. So let us see what are the traditional optimization methods. So linear programming, nonlinear programming, integer programming, quadratic programming, stochastic programming, dynamic programming. These are the 6 methods comes under traditional optimization. I think there are some other methods also there. Mathematics teachers can know this. So I have listed out some 6 methods under this traditional optimization. So these 6 methods having some limitations. I will tell you what are those limitations. Okay, so due to overcome those limitations, we are going for non-traditional optimization. So in the non-traditional optimization, we are having so many algorithms are there nowadays in the literature. But I have listed some 6 algorithms which I have worked out in my research. Okay, so genetic algorithm, PSO algorithm, BAT algorithm, cuckoo search algorithm, Jaya algorithm, TLBO algorithm. So these are the 6 methods I have listed out. Apart from these 6 methods, there are some other methods also available in the literature. Okay, so now let us discuss what are the limitations of traditional optimization. So in the traditional optimization, if a function is a nonlinear function, okay, if a function is, let us assume a function is nonlinear function. So nonlinear function means it is having some various maximal points and various minimal points. So when we are using, suppose we are using linear programming method. So when we are using linear programming method for the nonlinear function, what is happening? The first maximal point in that function is considered as the maximum point. Suppose we are doing maximization problem. Okay, suppose we are doing maximization problem using linear programming method. So the first maximal point will be taken as the maximum point for that function, but it is not considering the global maximum. Okay, there is one more maximum which is maximum than this that is the maximum taken by linear programming method. So that means the linear programming method or any other traditional method is getting stuck in the local minima or local maxima. So we are not getting global minima or global maximum point using these traditional optimization methods. So that is the basic disadvantage of the traditional optimization methods. So they are getting stuck at the local minima or local maximum point. So they are unable to catch the global maximum or global minimum. So that is the basic drawback of the traditional optimization methods. Why? Because why they are unable to catch the global optimum point? Because in the traditional optimization methods, we are starting the searching process from one single solution. From one single solution, we are starting the searching process. So as the iterations proceeding process, as the iterations increasing, this solution is updating iteration to iteration. Okay, so it is unable to catch the global optimum point. But whereas in the case of non-traditional optimization, we are using multiple solutions. We are using the searching process from the multiple solutions. Okay, we are using searching process from a multiple solutions. So this multiple solutions is nothing but we are calling in the optimization language, we are calling it as a population. In the optimization language, we are calling as a population. So all these non-traditional optimization methods are using a population search based technique. So that means that when some 10 solutions, let us say 10 solutions are starting searching process, then then at least one solution can catch the global optimal point. So that is the basic advantage of the non-traditional optimization. So nowadays, for all the nonlinear functions optimization, we are going for non-traditional optimization methods. Okay, one live example I can tell you. In Japan, when they are designing the train, this magneto-leviation train, then they have used the genetic algorithm for the designing shape of the that engine head. Designing the shape of the engine head, they have used the genetic algorithm optimization. So like this, there are so many practical examples. So few examples I can know, and there are some other examples are also there in the society where we are using non-traditional optimization methods. Okay. So this is the basic difference between traditional optimization and non-traditional optimization. So in the traditional optimization, we are unable to catch the global optima. But whereas in the case of non-traditional optimization, we can catch the global optima. Now in this non-traditional optimization, the basic algorithm is genetic algorithm. So this I want to introduce to you. So then the genetic algorithm was developed by John Holland, University of Michigan in 1970. The GA is a search-based optimization technique based on the principles of genetics and natural selection. So this is the basic principle. So it is frequently used to find the optimal or near optimal solution for non-linear problems. Okay, that's what I told you. For non-linear problems only, we are using this genetic algorithm to find the optimal point. Okay. Now let us say the fitness function for the maximization problem. Okay, let us say my problem is maximization. Okay, we can do maximization or minimization. Okay, but let us assume that we are going to do maximization. Okay, so the fitness function for the maximization problem is f of x is equal to capital F of x. Okay, and minimization problem and for minimization problem, the fitness function f of x is equal to 1 by 1 plus f of x. Okay, so here small f of x is the fitness function and capital F of x is the objective function. That means for a maximization problem in genetic algorithm, your objective function is equal to fitness function. But for a minimization problem in genetic algorithm, your fitness function is equal to 1 by 1 plus objective function. So why we are doing like this means genetic algorithm can do only maximization. It is the property of the genetic algorithm. It can do only the maximization. So for a maximization problem, your function, the function which we are going to maximize, that will be the objective function. So my fitness function is directly equal to the objective function. But for minimization, using genetic algorithm, how we have to do? So I want to convert into a 1 by 1 plus f of x. So that is treated as my fitness function. So in the process of this fitness function maximization, that means 1 by 1 plus f of x, we are trying to do maximization. That means what is happening? Capital F of x is minimizing here. So I am trying to maximize the total function, total whole fitness function, that is 1 by 1 plus f of x. I am trying to maximize. So in this process, capital of x is minimizing. So this like this we have to consider for maximization and minimization. So here optimization is the basic process of making something better. So we will be having, we'll be giving some inputs, set of inputs to a process, then we'll get some set of outputs. So this is called as optimization. Nature has always been a great source of inspiration for mankind. So GS are search-based algorithms based on the concepts of natural selection and genetics. So this is basically developed from the concept of natural selection and genetics from the human beings. So GS are subset of much larger branch of computation known as evolutionary computation. So evolutionary computation is a big subject. So it is a big ocean. So in that, GA is a small topic, okay, in the evolutionary computation. So what is the basic algorithm for GA? So these are the basic steps. 7 steps are there for in the algorithm of GA. The first one is select encoding type. Okay, the encoding type means whether we are using a real encoding type or binary encoding type. So that we have to decide first. Then second, choose population size. Then third, randomly choose initial population. Fourth, select parental chromosomes. Then fifth is crossover and mutation. Sixth, evaluation of offspring. 7, if stopping criteria is not reached, then again go to step 4 and repeat the process. These are the basic steps of genetic algorithm. So I want to explain in the further slide each stepwise. So first of all, let us see some basic terminologies used in the genetic algorithm. So here we are using population. Population means it is a subset of all the possible encoded solutions to the given problem. So it is nothing but it is a subset of possible solutions, okay, which we can apply to the problem, given problem. Next, chromosome. A chromosome is one such solution to the given problem. So a chromosome is nothing but it is a one solution from the set of solution. That means a chromosome is the one solution among the population. Okay, among population means it is a set of solutions. In that one solution we call it as a chromosome. Next, gene. A gene is one element position of a chromosome. So gene is nothing but it is a one element in the chromosome. Allele. It is the value of gene takes for a particular chromosome. Okay, it is the value of the gene in the chromosome. So that is allele. Now here, like this is the representation of genetic chromosome. Okay, this is the genotype representation we will call it as. So it's nothing but a chromosome representation. So in the binary representation, if you select a binary representation like this, we have to give the digits, binary values 0, 0, 1, 0. Like this, we have to generate the binary chromosome. If I are using real valued representation, then like this, we have to give the real values genes. So each bit is called as gene. So okay, each value is called gene. So like this, we have to generate the genes for the real valued chromosome. So here I have taken floating point values 0.5, 0.2, 0. We can use integer values also. Okay, in the binary, in the real value, here I have used floating point values. Okay, we can use integer values also, no problem. Okay, based on the requirement of the problem, we'll use either floating point values or integer values. Okay, but in today's presentation, I am going to use only binary representation. I'm not going to use real value representation. Okay, so here I'm using in this presentation binary chromosomes only. So like this. So this is a matrix. So in this matrix, we are having a set of chromosomes. That means the total all chromosomes here we will call it as a population. So the set of chromosomes we will call it as a population. Here you can see in this slide clearly it is written. Okay, all this set of chromosomes is called as population. So in this, now we will select one chromosome. That is the second chromosome where suppose I have selected. So second chromosome is having values 0, 1, 0, 1, 0, 1, 0, 1. So each bit is called as gene. Each bit is called as gene. The value of gene is called allele. So here you see, so this is the chromosome. Okay, this chromosome I have again represented separately here 0, 1, 0, 1, 0, 1, 0, 1. So in this I have taken third gene. Okay, third bit. So this third bit is called as gene. So the value of the gene is here 0. So that 0 is nothing but allele. Understanding? So now let's go to fourth position. So fourth gene. So the value of the fourth gene is 1. So that is the 1 is allele. Okay. Now I am going to an example. So with this example, I will explain you the total algorithm. So here my problem is my example is maximizing the function f of x is equal to x square, where x is the having the range 0 to 31. Here the x value ranges from 0 to 31. Okay, this is the basic representation of the problem. Okay, so here this problem is single objective, single variable problem. Okay, that means here only I am having only one variable, that is x. So single variable, single objective function. Here it is. Okay, so we have to give the range of the variable. Always we have to mention the range of the variable. Otherwise, genetic algorithm cannot work. Okay, we have to mention the range of the variable. So the range of the variable of the x is 0 to 31. Now here my objective function is f of x is equal to x square. Now my fitness function f of x is equal to objective function capital F of x, because it is a maximized problem. As in the previous slide I told you, in the maximized problem, capital F of x is equal to your fitness function f of x. Now I have to consider, now I have to choose a encoding technique. Okay, encoding technique I am using here binary technique. So my range is 0 to 31. So the minimum value is 0, maximum value is 31. So for 0 I have represented like this with 5 zeros. So for 31 I have represented like this with 5 ones. Okay, so that means I am taking 5 bits to represent the values between 0 and 31. Now let us select the population size. So that is nothing but number of chromosomes, that is number of solutions. So population size is equal to 4 here. So that, let us say that is capital N is equal to 4. Now randomly choose initial population in binary bits and then decode that string. Okay, now what we have to do is, see here, next table I am going to explain. So string number it is 1, 2, 3, 4, that is nothing but population number. So minimum value is 0, maximum value is 31 for x. So between 0 and 31 only we have to generate the population. So, and the population, how many bits I have used? 5 bits I am using. Okay, I'm using only 5 bits. So with these 5 bits I want to represent the values between 0 and 31. So here you see the first chromosome. See the selection of the chromosome is, again it is randomly. Okay, we are taking randomly only. Okay, that's why step 3 is randomly choose initial population in binary bits and then decode that string. So here I have chosen randomly some 5 bits. Randomly I have generated some 5 bits. Okay, now I will decode that value. So when I will decode that value, in the decimal value we are getting 13. Next, similarly, second chromosome, I have generated some random bits, that is 11000. So this is the randomly generated. Okay, now I want to decode that. So we are getting 24. Like that, 3 for the third chromosome I am getting 8. For the fourth chromosome I am getting 19. So next, this is the decoded value. Next is the x actual. So x actual, here you see both are same only. But in this example I have taken like this. But in some other examples, what will happen? Sometimes the decoded value is the out of range. That means it is more than 31 also. Sometimes we may get. So it will be the out of range. We may get out of the range. So to bring that value within the range of my variable, I am using this formula. X actual is equal to x min plus x max minus x min by 2 power n minus 1. Okay, into decoded value. This is the formula we are using to calculate the x actual. Okay, so where 2 power n means here n is nothing but the string length. So what is string length? String means here the chromosome length. So here we are using 5 bits. Okay, so n is equal to 5 here. So x min is 0 plus x max means 31 minus 0 by 2 power 5, because I am using 5 bits to represent my chromosome. That is called a string length. So 2 power 5 minus 1 into decoded value. So decoded value is 13. So again we are getting 13 only, because it is in the, so that my decoded value here is already within the range. Okay, already within the range. So my x actual is not changing. But if my decoded value is out of the limits, then we have to bring that, we are using this formula, we have to bring that within the limits. Then the x actual value will differ. Okay. Now I want to calculate f of x value, that is fitness function value. So in the f of x value, what is f of x? What is my function? That is x square. So here you do the whole square for all these x actual values. So I am getting 116, 576, 64, 361. Now next step. So next step is called is elitism. So in the elitism, what we are doing is the chromosomes are arranged in the descending order of their fitness value. So here I am having 4 chromosomes. So all these 4 chromosomes are arranged in the descending order of this fitness value. That is f of x value. So here you see, the highest value is 576. Next second is 361. Next third is 169. Next fourth is 64. So like this, I have arranged it. So based on this f of x value, that is fitness value, I have arranged in the descending order. Now, here I am taking elitism probability P is equal to 0.2. So what is this elitism probability? What is the significance of P equal to 0.2? So here, the elitism probability significance is, as the elitism probability 0.2, that means 20% of total chromosomes will be sent directly as children for the next iteration. Okay. So this is, we are doing first iteration here. So what I am doing, I have taken elitism probability 0.2. So that means 20% of these 4 chromosomes. So here 20% of 4 chromosomes 0.8, which is almost equal to 1. That means my first chromosome, that is 11000, whose value is 576, is directly forwarded to next iteration as a child, as child 1. Okay. So this chromosome 1, this 11000, whose value is 576, this chromosome is directly forwarded to the next iteration as child 1. Okay. So in the next iteration, how many childs I have to generate? I have to generate another 3 children. So to select so next step is to generate the children, the 3 children for the next iteration. We need parents. We know. So you know, in the natural process also, human beings also, to generate children, we need 2 parents. Okay, so here also same concept is applied. So selection of parents we have to do. So you can ask a doubt. So why we need to select the parents? Okay, so what is the main necessity of selection of parents? So the main necessity of selection of parents is, here you see in this previous table, 1, 2, 3, 4 are all eligible for parents only, are all parents actually. Okay, but here I am selecting only few parents. Okay, not all. So why like that we are selecting only few parents? Means the parents which is having highest f of x value, that means those parents are having, will produce the better children for the next iteration. So that is the main significance here. The parents which is having better fitness value, those parents I am selecting to produce a better children, the strong children for the next iteration. Strong children means here nothing but a strong chromosome. Okay, so that's why we have to select the parent. So in the selection of parental chromosome, various methods are there here also. So first one is Rowlett-Will selection, second one is tournament selection, third one is rank selection. So like these 3 methods are there for the parent selection. So here I am using Rowlett-Will selection. So nothing but you may have seen in some English movies this Rowlett-Will. There is a game called Rowlett-Will. Okay. So this is a Rowlett-Will. Here we use Rowlett-Will selection method for selecting parental chromosome. So let us see what is this Rowlett-Will selection method mathematically. Okay. In a game point of view, we know we'll rotate the wheel and it will stop at some point. Then that value will choose. But how we model that is mathematically. So here you say this is a table. My x min is 0, x max is 31. So these are the string numbers 1, 2, 3, 4. Okay, this is the initial population. This is the decoded value. This is the actual value. Okay, these are already I have explained. So this is the f of x value. Now, so up to this f of x value is same as the previous slide only. Now, next another parameter I am adding, that is probability count. So probability count is nothing but f of x value by total value. So this f of x values, I am adding all the f of x values and calculating total value, that is 1170, and I am calculating the average of all these 4 f of x values, that is 293. Okay, just remember this. Now probability count is f of x value by total value. That means here you see 169, that is the first chromosome, f of x value is 169. Total value is 1170. So 169 by 1170, you are getting 0.14. Like that. 576 divided by 1170, you are getting 0.49. Like this, 0.06, 0.31. And finally, Then when we add all these probability counts, we have to get 1. Okay, that is the, that you have to remember. If you're not getting 1 as the sum, as if you're not getting 1, that is the sum of the all probability counts, you have done some mistake somewhere. Okay, this is the verification procedure. So this is the verification step. Okay, if you're not getting 1, that is sum of all the probability counts, it should be 1. Okay, if you're not getting 1, that means you have done some mistake somewhere. Again you have to check. Okay, again you have to check back. So here I am getting 1. That means till now everything is okay. Okay, next is expected count. Expected count is FFX value by average value. So FFX value is 1769 divided by average value, so 293. I am getting 0.58. Like that I have calculated all the 4 values. Then I have to add all these values. I am getting 4. Okay, I am getting 4. So here I have to get, because here I have to get 4 only. That means because my population size is 4. Understood? My population size is 4. So I have to get the population size value only. So I am getting 4. If you are not getting 4 means you are doing some mistake somewhere. Again you have to check back. So these are the verification steps. Okay. Next, actual count. So here expected count is 0.58 means it is almost equal to 1. Next, expected count 1.97 means here actual count we can take it as 2. 0.22 means 0. 1.23 means it is rounded to 1. Okay, that is the actual count. So now you see here, when I am rotating my wheel, roulette wheel, that means string 1, the selection of string 1, the probability of selection of string 1 is 1 time. But when I am rotating roulette wheel again, the probability of selection of chromosome 2 is 2 times. But my chromosome 3 is not getting selected in the roulette wheel because it is a weak parent, because its value, its FFX value is the least, that is 64. So it is a weak chromosome. So this weak chromosome is not getting selected in the roulette wheel. So that's why its value is 0. Then 4th chromosome, it is getting selected for 1 time when we are rotating the roulette wheel. That is the meaning of the actual count. Okay. So here you can observe the 2nd chromosome is getting count 2. That means it is a strong chromosome. That means it is a strong parent. Okay. So what we will do is, from the next step, we will go for crossover. Okay. So here in the previous slide, selection of parents is over. That means first chromosome, 2nd chromosome, 4th chromosome. These are the 3 eligible for parents for the crossover, for the next step. Okay. My chromosome 1, chromosome 2 and chromosome 4, these 3 chromosomes only are eligible as parents for the next step in the algorithm. So what is the next step? Next step is crossover. So for this crossover, the input is parents. So again, in the crossover, there are different types of methods are there. A, single point crossover, B, 2-point crossover, C, uniform crossover. Okay. So here, as time is limited, I am using only single point crossover. Okay. So the single point crossover I am using. So here I am taking a crossover probability PC is equal to 0.8 or 0.9 or 0.95. Here we have to take maximum value only, but it is less than 1 only. The crossover probability should be less than 1, but it should be close to 1 only. But it should be close to 1, either 0.8 or 0.9 or 0.95. Okay, based on our problem requirement there. Now, if rand means I am generating a random number between 0 and 1. Okay, rand means you remember that it will be generated between 0 and 1 only. So if my rand is less than PC, that is crossover probability, then perform crossover operation. Okay. Okay, let us say my rand is less than PC. So I am going for crossover operation. So in the crossover operation, I have to select 2 parents first. I have to choose 2 parents. So already we have selected parents in the previous slide. That is chromosome 1, chromosome 2, chromosome 4. So chromosome 2 times it is selected for parents. So I am using first chromosome 2, that is string 2. Then with this string 2, I am using string 1 as a combination for another parent. As you know, to produce a child, 2 parents are required. So here string 2 I am using as parent 1 and string 1 is I am using as parent 2. So you write so here I am writing the string 2 11 000 0 11 0 1. Okay, that is the chromosome value. Now what I have to do is, so what I am doing is, now I have to start the crossover operation. Okay, so in the crossover operation, what I am doing is, so this is a single point crossover. Single point crossover means we have to select a site selection. That means after four bits, after 4 positions, that is first bit 1. So you see, you just check string 2. In the string 2, first bit is 1, second bit is 1, third bit is 0, fourth bit is 0. So after 4 bits, I am drawing a line. Okay, I am drawing a line. Okay, similarly for string 1 also, after 4 bits, I am drawing a line. Okay, so this is, so after this line, what are the bits are there? In the string 2, 0 is there, in string 1 is there. So just interchange these 2 bits. Okay, after that line, that is the right side of that line, what are the bits available in string 2? 0 and string 1. So just interchange those 2 bits. So that is 11001. That is the first child. Then 01100. This is the child 1. So like this, children has generated. Similarly, another crossover. So here another crossover. So again I am taking string 2, because string 2 is selected 2 times. No, string 2 is selected 2 times as a parent. So here 1 time I have used. So again I am using second time. So again string 2 and string 4. Again I am taking same. After 4 bits, I am drawing a line. Okay. So after that line, in string 2 0 is available, and in string 4 1 is available. Just interchange those 2. Just wait. Here what we use, not after 3 bits. Sorry, after 3 bits. Here I have used, after 3 bits I have drawn a line. Okay, after 3 bits I have drawn a line. So the left side of the line is in string 2 110 and right side is 00. Similarly in string 4, the left side of the line is 100 and right side is 11. So just right side of the line, the bits which are available, just interchange those. So if you interchange like this, what will happen? You see, in the string 2, 110 is the 3 bits which are available left side of the line. So after that line, 00. So that will be interchanged. So in string 4 we are having 11. So that 11 is replaced here. So we are getting 11011 as child 3. Next in string 4, 100 is the right side of the line. Left side of the line. So right side of the line is 11. So this 11 is replaced by 00 of the string 2. So 140, that is child 4. So like this, children are produced. So but here we don't require child 4 because we are using LTSM operation in this method. So we want only 3 childs. Already 1 child is generated in the LTSM. Okay, so we need only 3 childs. So child 2, child 1, child 3 we need. We are neglecting child 4. Next step is mutation. It's almost over. Another 5 minutes it will be completed. So next step is mutation. So why we are performing mutation? Here we have children, child 1, child 2, child 3 already generated from the nested result. Then what is the necessity of mutation? So the necessity of mutation is, there are chances sometimes there may be chances that your child 1 or child 2 may generate in a same manner. That means the child 1 and child 2 may get a same value. Okay, child 1 and child 2, both the childs may get same value. That type of chances will be there. Here, of course, here in this example we got all the 4 childs different. But in some examples, there are some chances that my childs which are generated. So in those childs, any 2 childs will have same value. Any 2 childs may get same value. That type of chances may be there. So to avoid that type of problem, I am using mutation operator here. Okay. So what is mutation? So mutation is performed for each bit of chromosome in the child. So okay, mutation is operated not for the whole string. Here it is mutation is performed bitwise in the child, which is generated in the crossover. So here I am taking mutation probability is 0.3. If my rand, again I am generating a random number between 0 and 1. If my rand is less than mutation probability, then flip that to bit. Okay. So here you see the example. So my child 1, what is the child 1 generated here? child 1 is 0, 1, 1, 0, 0. This is the child 1 generated in the crossover. So 0, 1, 0, 0 I have written as child 1. So now I am taking a random value. Okay, that is rand. So random value I am generating for each bit. That is 0.2 for first bit, 0.9 for second bit, for third bit 0.5, then 0.1, 0.7. Then next you check the if your random value is less than your mutation probability. So here 0.2, that is first bit random value, 0.2, that is less than 0.3. So just flip that bit. So 0 is converted to 1. Next bit is 0.9. So it is greater than PM. So no need to change. Just 1 you are keeping it as it is. Next 0.5. So don't flip it. It is greater than PM. Like this. So like this we are getting actual child 1. Similarly, actual child 2 for child 2 also. Okay, in child 2 also. So what is child 2 in the crossover? 1, 1, 0, 0, 1. So here also again I am generating a random values for all the 5 bits in the child 2. So again I am checking which random value is less than my mutation probability. For that random value only I am converting the I am flipping the bit value. So here you see first bit 1 is retained as it is. The second bit 1 is random value 0.2 which is less than 0.3. So I am flipping it. So it is converted to 0. Next fourth bit, third bit is retained as it is. Next fourth bit retained as it is. Next again fifth bit, that is 1 and its random value is 0.1. It is less than 0.3. So flip it because 0.1 is less than my PM 0.3. So again you have to flip it. So the 1 is converted to 0. So actual value we are getting 1, 4 zeros. Similarly, the same procedure is done for child 3 also. Okay, I am neglecting child 4 because in the elitism I have already copied one child to the next iteration. So I need only 3 childs here. Next step 8, this is the last step. Evaluation of child or offspring. Now I got all the 3 childs, that is actual childs. So here this is first string numbers I am writing 1, 2, 3, 4. Next the actual childs. Okay, actual childs I am writing here. Okay, so what is the actual child? So my actual child 1 is 1, 1, 1, 1, 1, 0. So that is 4 1s 0. So here you see 4 1s 0. Next my actual child 2 1 4 zeros. So here 1 4 zeros. Next actual child 3 1 0 0 1 0. So 1 0 0 1 0. Next this child 4. So this came from my elitism. So elitism here I have used the one chromosome I have forwarded to next iteration here. So that is what is the that one chromosome is nothing but the best chromosome. So here best chromosome is my problem is maximization. So I want a maximum value. So the maximum value is 576. So so corresponding to 576, the chromosome is 1 1 0 0. That is the first chromosome in this table. So this chromosome is copied to that means forwarded to next iteration as a child. So this 1 1 0 0 I am taking as here child 4. I am taking as child 4. Now again I am decoding all these values. So I am getting 30, 16, 18, 24. Now you can check whether all these x values are within the limits or not. So because I have given the range is 0 to 30. So all the values, all the 4 values are within the range only. Then you calculate the f of x value, that is x square. So for 30, x square is 900. So for 16, 256. For 18, x square is 324. For 24, x square is 576. Now you can see. So here notice string number 4, that is child 4, came from elitism. Okay. So here you see 900 is the maximum value I am getting here. So there is some improvement in the process. Okay. So initially where I started, my initial population where I started, I got 576 is the maximum value in my initial population. Now coming to the end of this iteration, that is we are getting the maximum value here, we are getting 900. So these 4 strings will be evaluated for the next iteration. For iteration 2, again we are using these 4 strings. That means these 4 childs will be evaluated for the next iteration. Again the same process will be continued for the second iteration also. Again same selection, cross combination. Again we will produce at the end of second iteration. Like this, iteration by iteration.
Sir,
and finally,
is not clear, sir.
And finally, we will get the maximum value. So here, oh, so last slide. So this is a basic genetic algorithm. I hope you have understood. So some application areas. Mainly we are using basically, as I am an electrical engineer person, so I have highlighted my electrical engineering. So here we are having genetic applications in all the domains. So in electrical engineering, we are using for power system optimization and for machine modeling. We are using this genetic algorithm. Similarly, in the mechanical engineering also some machine parameters optimization they are using. Similarly, we can use genetic algorithm in civil engineering. Similarly, we can use genetic algorithm in computer science engineering. And also we are using genetic algorithm in electronics engineering. That is my co-research fellows, research scholars, they have worked for patch antenna design and its optimization. In this domain, they have used genetic algorithm. Okay, so like this, we can have applications of genetic algorithm in all the 5 domains. Thank you.
Thank you very much, sir,
for giving me this opportunity.
Thank you, sir. Thank you. I thank you all the participants for your patience and supporting us to continue this lecture series. Okay. Good evening to all. Okay. So we'll come back again tomorrow, please. Okay. With this, I will end the session.
Thank you, sir.
Okay. Thank you, sir.